should know today. Not Venezuela. Okay, let's go, let's go, let's go. And go. Okay. We are now going, and I could say I made no errors here whatsoever. I don't know what anybody is talking about. I'll draw it in a different color. And now our nitrogen should go down, and that would be 2 levels. Our hydrogen should go up by 3 levels, so that might be a fair bit. Let's make, which one's the most? 3? So let's make this one 3. And then that one's 2. And then that one is 1. Not very much at all. Because I didn't give myself very much room. 3x, 2x, 1x. In terms of the amounts. So we're going to shift towards the side. If you decrease the pressure, you shift to the side with the most molecules, particles. If you increase the pressure, which way would it shift? To the right, where it has less particles. It would try and offset that change. Oops, sorry. Anybody still writing that down? This is where I try to actually just show it graphically. So, I have a box. It's literally a box of happiness because it's full of stars and smiles. If I have like that and I then decrease the size, everything's become more concentrated. So I can make the same amount of particles in proportion before. If I take away 3 stars, shift to the other side, and put in 2 happy faces, and then I do that again, now it kind of looks proportional to what it was before. I've decreased the number of molecules, I restored the pressure back to what it was, even though because gases don't care what the particles are, they're just adding to the pressure. So if I make it super big, get all these things out of there, and it's got to fill the space. Now it's going to shift the other way, so it's going to make 3 stars for every 2 happiness. Do you get my star to smiley face analogy? Apparently I have an old Flash animation. Flash, if you don't know, was an old method of showing things that took over your computer, and eventually people realized it was bad because viruses. want to increase the pressure or decrease the pressure? Increase the pressure.
You have increased the pressure by decreasing the volume of the container. The system can partially offset this stress by decreasing the moles of gas. Recall that pressure is directly proportional to the moles of gas. Because of the 2-to-1 mole ratio in the balanced equation, the moles of gas can be decreased if the system shifts to the left, producing iodine molecules and decreasing the number of iodine atoms, as you can see in the microscopic view. As more iodine molecules, which have a purple color, are produced, the color of the equilibrium mixture darkens. This can be seen in the macroscopic view. Note that the total number of gas particles has decreased.
Yeah, you can stop talking. So, graph the concentration if the volume is decreased for this particular reaction. Will it shift towards reactants and products? And graph it. Fill in the blank. I'll do it with 10. We've got Dojo. 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's one person missing. Elena. That's terrible. I think if that watch existed here, like it does in Harry Potter, where you could just stop time, people would just show up to class, they'd start doing things, and then they'd come back later and they'd be like 10 years older because of all the games and sports they did in between, and they were finally done. I was counseling someone last night trying to find time where they can get their work done, and they had so many things to be at that they were panicking because they couldn't make an appointment to find the time to do the work, to organize the time. That's difficult. Now that I've done that, we've looked at it, this wouldn't be bad for you. Even for your, what? No. Where's that? Plug in. What are you doing? Do you know there's spy software, like virus software you can get on your computer? What they've encoded with an algorithm is it will listen to you type and record what you type. So it's just using your microphone as you type and just listening. And eventually it will figure out what sounds correspond to what letters based on the time it takes to sound of the keyboard, the time your fingers hit it on average, and then over time it can then know your passwords even if it's entered in a way that bypasses that. Because you'll do it in a particular rhythm. It's the future now. I think groups of 2. Excellent. To the board. Graph that sucker. You've had a few minutes to do it on your own. And erase what's ever there. Marcus, are you okay?
I'm okay.
How early was your early morning walk?
I didn't have
You didn't even have an early morning walk?
No, I'm tired.
You went running?
I was just up late today. Same mark.
Sure.
I like looking
Sure you were.
Never do that.
Yeah, you're probably partying.
If he was partying out here. I was there.
Should I put the page back? You,
remember what it was.
there's the page.
Wait, what? Yeah, okay.
There you go.
Okay, so NO. Yeah, yeah, yeah. Okay, so it shifts all three options. So it goes. Yeah, what's decreasing?
Where am I from?
I'm pretty sure I have it. So I'm just gonna go over. Order in different I'm pretty sure.
As long as, yeah.
Oh, don't. As long as you're above the lines.
Yeah.
I've been told I'll get shot. There's also the little white ones if you want to use them at the back, but that's fine too. It, just a black one here sometimes. I should get light colors for that.
I don't think they all go down. NOCL is gonna go down.
So we're going to decrease the volume. And do I need to get another balloon? Oh, we got some arguments. Excellent. Mm. Take a look at other people's. There are some that are really good in one area and a little different in another, and some, but they get like one fundamental. You have a mix of right and wrong answers. I do feel like maybe getting the balloon. Oh, some have corrected. That one corrected. That one corrected. Half of them are incorrect. Better, because you had it the other way around before, I think.
No.
I think everything was going down at one point. No, it never happened.
We discussed that.
Oh, we discussed that. Okay, you changed it. Excellent. Well done. Okay, and which way do you have it going to? So yeah, it's going to go. So NOCL. Oh, that's going to go over there. And then those ones going to go up. That's looking good. Yeah. That's looking good. Once you think you have it, you can have a seat. Fill in the blanks.
Yeah. No, you're good. And then that one's one, and then this one's one.
Would it not be this?
Well, with gases, because you make a change in volume, you're going to have straight lines right away. They're all going to change all at once. So there's no slope to them. And one can't go up with the other down. Because you can't change half the volume up and half the volume down. It's the whole container. So one of the things you're going to see with a change in volume is they all spike up or they all spike down. And if we decrease the volume, what have we done to the pressure? Increase. So we have increase in pressure, increase in pressure. This is a decrease in pressure, increase in pressure, decrease in pressure, decrease in pressure, and one adjustment that was independent. Decrease in pressure. And that is a volume decrease. So don't forget, volume and pressure are inversely proportional. So when volume goes up, pressure goes down. When volume goes down, pressure goes up. And pressure is another way of saying concentration. So if the volume is decreased and the pressure is increased, that means they should all spike up. Okay. And then, if they all spike up, which way are they going to shift to undo that spike, to have the most things going away? That way? That way?
Wait. Because the pressure is decreasing, it's going to
We increase the pressure. How could we decrease that pressure?
if
We want to go it that way. So our NOCL should go up by 2. And then our NO should go down by 2. This is now going to get messy. Because come on, let's make that a different color. We got orange or red. There we go. And then our Cl2, shifting away, should go down by 1. So by increasing 2x, we actually get to go down by 3x. So you actually can see it in the change. And now we have new equilibriums in this spot. So it shifts towards reactants.
But it
Wait, what?
wants to go to the product.
Sorry. It wants to go to the products, so it shifts towards products. I do the same thing sometimes you do. On this, which side is the reactants?
Left side.
The left side, always. We define it that way.
Wait, but I thought because of the energy, like, because isn't that?
Did we change the temperature?
Oh, so it doesn't.
Doesn't matter. Yeah. So there will be questions like, what could you do to shift this reactant to the right? And we would say, decrease the temperature and decrease the volume and increase the concentrations of NO by injecting some in. Like, you can do multiple things, but for this one, we're only changing the volume. So the energy doesn't matter.
Okay.
Why do you want it to matter?
No,
Okay.
because I'm just having a hard time like picturing like which side it's going to.
If the pressure is increased and the volume is decreased, the reaction will shift to the side with the most, fewest.
Oh,
If the pressure is increased, we want to go to the side with the fewest. And it doesn't matter what their identity is. It's just a matter of the fact that we have 3 on this side and 2 on that side. And energy is not a particle, so it doesn't get counted.
So that's just like the rule. That
Yeah, that's just the rule. Now, I didn't put it in here, but especially given that we have a quiz, if I was to look at the rate over time t1, and I've got forward and reverse rate, they're the same until that time. We'll make red forward, blue reversed. When I decrease the volume and increase the pressure, what happened to the rates?
they go up.
They go up. Both?
Just the four. Right.
What
Oh,
increase?
wait, no.
All of them increased in concentration, so they all went up. But which side increased concentration the most?
Reactants.
Reactants. And that's actually fundamentally why it shifts. This side has the most stuff, so it increased the most. So the side that has the most stuff is most affected by changes in volume because of changes in concentration. And so the forward rate, which I mean red, spikes the most, and the reverse rate spikes the least. And then as it shifts, what happens to the forward rate? Goes down. And the reverse rate, as it receives more and more stuff, will slowly go up. And so you end up getting back to equilibrium over time when they are the same. So there's 2 different explanations you can always give for these. You can always give the Le Chatelier's principle, which is whatever you do, nature tries to undo, or the system will change in a way to counteract the stress. The stress here was an increase in concentration due to an increase in concentration / pressure due to a decrease in volume. The Le Chatelier's principle would say you shift to the right in order to offset that stress and decrease the pressure. The rate reason would be the forward rate had the highest increase in concentration, so it increases the most and shifts the reaction to the other side until it rises to match and it decreases. Identify the effect of a catalyst on equilibrium. Concentration. Not even going to tell you. No. Works better than this two. Go. You don't even have to label that much. Just draw what you think they would look like. What's your best guess? What will a catalyst do? Look at both sides of the reaction. You add a catalyst. What happens to the concentrations? Anybody still need another partner? Fast, draw it, sit down. We'll see who gets it right. Jacqueline, are you going to stay under there the whole class?
Yep.
Isn't it hot?
Nope.
Okay.
Cold in here.
What? I'm literally sweating.
I'm wearing like 4 layers now, so.
Really?
That doesn't do
Are you normally in a hot country?
I'm in California, so it's
Oh,
not
okay.
like hot, but it's also not cold like
It'll never
here,
get
though.
cold. There was one poor boy from Mexico who, after a while, was just like, I really like coming to school here. And now, whenever I go to Mexico, I'm too hot. And when I go to Canada, I'm too cold. I never get it right.
Hey, Mr. Boss.
Oh, don't wave it. You don't disturb other people. What are you doing? Okay, quickly draw the graph. What it's going to look like if you add a catalyst. You don't have to worry about x's or anything. Just proportionally what you think will happen to either side. AB goes to AB. A plus B goes to AB. What will a catalyst shift? What's different?
Nothing.
Okay. Did you draw that?
Well, all increases but the same.
With you're drawing concentrations, not rate. Okay. So all the concentrations go up? Yeah, because where could that come from?
Yeah, but the catalyst increases the amount of fluid.
It doesn't. It will definitely increase the amount of fluid.
Wait, I remember reading it.
Okay, once you got it, have a seat.
Stay straight.
I did ask you for the concentration. I will do rate in a second. Ooh, nice. More people got on board. If you add a catalyst, it makes the reaction go faster. So the forward rate will definitely go faster. What will happen to the reverse rate? Also go faster. A catalyst increases the rate of both by equal amount. So you see no change in an equilibrium. So all the ones with straight lines, you're good. For all the ones where they all went up, you didn't add anything to the system. Where did it matter? You just broke the law of conservation of mass. Where did that come from? No volume change, didn't do anything. You just added stuff as if by magic. It was Harry Potter. So you get no change. So a catalyst doesn't make a change in the system. If red is forward and blue is reversed, and once again purple is both same, what would the rate one look like? Add a catalyst. It would increase? Would one increase more than the other? No, so he just goes up and then keeps going. Oh, that's drawn in a shifty way. Up and then straight line. So a catalyst doesn't do anything to the equilibrium. It works by lowering the activation energy. So a reminder, it goes from something like this to something like this, but we still have the same delta H, and it lowered it for both sides. So it became easier for each of them. So they increase by an equal amount in terms of rate. So a quick system in equilibrium stays at equilibrium if a catalyst is added. Good. Am I still writing that down? Okay. You said I had another question.
Justin's wondering with the last box, if not at equilibrium, would reach equilibrium more blank.
More blank. If it's not at equilibrium, it would reach equilibrium more quickly. Thanks for pointing that out. Forgot about that. So all a catalyst will do is ensure it gets to equilibrium really fast. So it's not going to give you more product or more reactant. It's just going to give you more of both more quickly. Which is why industry is often first get a catalyst, but then second, how can you shift the equilibrium to the products that you want? Good. Now, commercial process. I think, no, let's do the commercial process. This is the Haber process. I will post a link to a reasonably good podcast on the story. It is an awful story in many ways. So I used to play it in class, and now I think it's too depressing. But just so you know, Mr. Haber invented the process. He did it not to feed the world, but he did it to make more bombs for Germany. This was in World War I. He also is the father of gas warfare, and possibly the reason why the Canadians really encouraged the invention of the ones that stop you from doing bad things in war. What's that called? Articles of... Yeah, the Geneva Convention. Canadians are responsible for a few of those.
Why can't we listen to it?
Pardon?
Why can't we listen to it?
It's really depressing. He was one of those, like, I work all the time and I don't pay any attention to my family. Brilliant chemist, invented the Haber process. Well, first invented gas warfare, to which was released on Canadians. I can't remember the name of the field. We did reasonably well against gas war, being the first to experience it compared to the Algerians, and there's another nation beside us, whoever the British didn't care about had put there. Canadians recognized the smell of chlorine from drinking water, because our water is all chlorinated because we're in a very rural country and you got to kill the bugs. So they recognized, oh, we use that to kill stuff in our water. It's probably trying to kill us. So they covered their mouths with a variety of things and eventually figured out, like, if you urinate on a piece of cloth or even just put water on it, you'll survive a bit longer. So Canadians actually did okay, which didn't help because they all died the next day in the counterattack. So after that, the Canadians were known for doing things like filling up a tin can full of food and throwing it to the Germans. And then the Germans would run and get the food and they'd be really happy. And then we'd do that for a week. And then on the 7th day or 8th day, we'd fill tin cans full of grenades and throw them over. And the Germans would run for the food and then they'd explode in their faces. They did night raids where they'd creep across enemy lines. And at night, they would then go into tents and silently kill as many people in their tents as they could. And then both sides realized this is actually kind of like not good. It doesn't give a lot of returns. And mostly it just makes everybody really upset. So we're going to say stop. And the Canadians disobeyed orders and kept doing it when everybody else stopped. We also continuously annoyed the Americans because we would take away their guns because they were too loud when they were doing night raids and they wanted to kill more Germans. Canadians did a lot of things, and I suspect it's because they were the first to get gas warfare. And so they didn't forget that for a little while. So he invented that, got recognized as a war hero from World War I, and then invented the Haber process. The Haber process made him an immediate war criminal by everybody else in the world, because if you can make this, yes, you can make fertilizer. Because once you have that, NH3 plus O2 in a variety of forms can make nitrates and nitrites, and you can make, and now you can feed your plants and they can grow and you can make a lot of food. What else do you make with nitrates? Bombs. Almost every reaction I've ever showed you in the fume hood that goes bang involves a nitrate of some kind. And so I tried to order really expensive fertilizer when I was a teenager because we lived on a farm and you can order tons of fertilizers. And I said, can you order this one? And he said, sure. And then it turns out they wanted to investigate him. He was like, you have to provide all these codes and paperwork, and why do you want to order this? He was like, I'm not ordering that. Because you could just take fertilizer, soak it in a little bit of diesel fuel, and you've made a bomb. You can blow up bridges with it. And I just wanted to grow some tropical plants. I didn't. I wanted to make a bomb. Like I knew what I was doing, and I was going to do that. And they won't ship it to the island without a ton of paperwork because you could blow up the ferry. And so bombs and fertilizer are essentially the same thing. So Fritz Haber invented this process, and everybody was like, well, he did it to make bombs, and so he was around the world. They did not like him. We used to get our nitrates for fertilizer and weapons like gunpowder from old bat caves, because bats would sit in caves and poop, and it would fall down and it would just accumulate. So wars were actually fought over bat caves because there were a large supply of nitrates. He also invented Zyklon A, which is the gas that they used in the concentration camps. They call it Zyklon B because his institute that he was given control of after World War I invented this. They went to the shelves in World War II and said, we need a chemical that can kill lots of people in a gas chamber. Zyklon B will do the job. Zyklon A, but it smells a little bit. We don't want them to know. So they took off the molecule that gave it a smell, and then they called it Zyklon B, and that's what they used. He's also Jewish, and he was in World War II when things started to get a little problematic for Jewish people. He ended up leaving, and nobody liked him around the world. So I think he ended up dying in a hotel in Switzerland. I'd have to double check the story again. It's probably on there somewhere. However, if he hadn't invented it, about 7 billion people, 6 billion people would probably be starving right now. You can't do modern agriculture without it. So he saved billions and billions of lives. When I say it's a sad story, his wife was a brilliant chemist. But at the time, you can't be female and a brilliant chemist at the same time. You can't have a job and be married. How are you going to serve your husband? So as soon as she got married, she was fired. She's not allowed to have it. She's the first woman in Germany to be awarded a PhD. It's really interesting how much of her work might be involved with the Haber process, especially because she was very upset afterwards at how it was used. And her writings indicate actually some of the work is probably hers. Like many brilliant women, they find someone else who's brilliant in the same field, and they work together. So a lot of her work might be in there. She was so upset that she left this world quickly, and after she did so, he just went to work the next day, left his son in charge, and basically didn't talk to him again. Because, you know, he had work to do. So yeah, it's a very sad story. But it's a super interesting story. So if you want to hear the whole thing in the podcast, I will post it. And it's interesting that this is currently what's feeding us. Because it wasn't for this, we wouldn't have enough food to eat. You can't grow enough food with traditional fertilizers. And to grow enough for everybody and keep prices down to the point that people can afford them, you need fertilizer. So you have this problem. You want this to go that way. Given pressure, temperature, surface area, what type of system, how can you make as much ammonia as possible knowing that this is an equilibrium? So it's going to make both. How can you get the most ammonia as possible? That one probably should be discussed in groups. What do you say? Groups of 3, 4, 4. No, 5 would be too many. No. 3, and then Hannah and Isabel can split up and join for a couple of floors. Find 3 people, see what you'll do for each one of those. Temperature, pressure, anything else you can think of to make that reaction go to the product side. It is pretty much a Halloween story, though. Erase what's ever on the board wherever you are. You don't have to work the board if you just want to consult at the table. I'm just going to ask each group for their ideas. One idea per group.
Okay.
If you increase the temperature,
Wouldn't you just change it? Not stupid. Change the temperature.
Why would you? Why would you? Okay, so you want to make.
I think I can go straight to bomb. Not food.
Wait,
No,
No, Fritz Haber would be
you
proud.
can just steal food with the bombs that you're like.
It's amazing how much human history reflects that process.
And you get more than food bombs. Because if you were to just make food, then you just got food, but you have bombs, you have power, and you
Yeah.
Decrease pressure. Close the system.
I'm so confused. What are we trying to do? The highest rate?
You want as many products as possible. So you want to shove the reaction to the product. You want ammonia. So you don't want hydrogen and nitrogen gas. You want to make,
I have no idea. I don't know if this is scenario or not. It just kind of says it.
Increase volume?
yeah, sorry. That would make it shift this way.
What about a catalyst?
So anything with a solid, what you'd want to like increase the surface area to make the rates go faster.
Could you add a catalyst?
So I like those words I put underneath. I think almost everything when I say discuss it. Do you have to worry about surface area with this one? No.
Wait, but could you add a catalyst or would that like mess it up?
Could you add a catalyst? No, you can add anything you like. So add a catalyst. You could add a catalyst.
So we're just, what are we trying to do here?
You want to make ammonia as fast as possible. Bred from air.
Oh, so you decrease volume.
Increase the temperature. Increase the temperature?
You have to decrease the temperature.
Decrease the temperature.
But pressure would work with that.
Matt, don't ask for what's for lunch or left. It's just sad.
But dinner's good. Dinner's like rigatoni and
Yeah, it's just
Matt, man, don't discuss it. That just makes me sad.
You don't get excited for dinners?
No, knowing that you just thinking about what's for dinner is more exciting than what you're doing now. Just
Okay,
thinking.
so, this is where I like green.
It's almost like.
So hungry. If I wasn't hungry, I would be very, very excited about chemistry.
But there was break and snack.
My brain isn't fueled enough right now to be thinking about like.
Okay, go to that cupboard right over there. Grab something to eat.
There's food in there?
Yeah.
Is there actually?
If you're very quiet with it, you can have some. Where's my pen? Nope, one over. One over. Open.
Wait, is this
What is there?
Yeah.
Yeah, no, that looks good. Yeah.
What do you want? Oreos, Milk bars, what do you want?
You want like?
Where?
Can I have the chewy? Can I have the chewy?
Oh, my bad.
Come on, man.
Well, that's it.
That's cat.
Guys, super guys.
Okay, I'm going to get you to stop in about 30 seconds. I want one thing from each group. So you should have a few things.
Oh, these
Quick, quick, quick.
break. Like the second break.
Nah.
Excellent. Okay. Good, the board will start with you. What's the first thing you would change?
I would wait.
Pressure, temperature,
I would decrease the volume
1.
by
Decrease volume.
by increasing the pressure.
Increase pressure. Yeah. If we increase the pressure, which way will it shift? It'll shift to the products. We have 4 particles to 2 particles, so that will work. Next one. Yep. Add a catalyst. Even, will that shift the equilibrium? No, but what will it do? Make it fast. Reaction go burr. Okay, I think the food is starting to become a little, just grab it quick. So hungry.
Can you pass through something, Evan?
So amazing. You have a quiz.
Also,
If you've done your quiz, you can go over this.
We're listening.
if you want.
Okay, over here. What group?
Something.
I was with them.
We had heat.
Heat. So high temperature, low temperature, what'd you come up with?
High temperature.
High. Which way will it shift?
That way.
Which way? So high temperature will make it go this way.
So low temperature.
Low temperature will slow the rate.
Oh. So no changing.
But it will slow the rate enough that you can collect it.
It will slow the rate enough that you can collect it. You could do this at like, there's actually, I was helping someone earlier today with their problem. They'll discuss this. It could, there are reactions that we do commercially that are done like at 1,000 degrees Celsius. And the reason we don't is because that temperature would shift it too far this way. So we don't actually want high temperature. High temp. It shift left. In 2 seconds since I talked to you, I've lost the pen, so I'm using my finger. If you have low temp, you have a slow rate. I mean, if you do it at room temperature, sure, you get ammonia, but you'll get like a tiny little thimbleful from a huge reaction vessel every couple of hours, and that's not nearly enough. So you just pick a medium temperature to adjust for both. And by medium, they mean 500 degrees Celsius. So that's a fast enough rate, and it's not off-shifted enough that you can still get products. It will be individual for every reaction that you do with this. You wouldn't have been able to guess like the degrees. So a medium temp, because you still want a faster rate. Anything else that we can do? Which group hasn't gone Yes, yeah. If it was endothermic, then you could just have high temperature. But one of the problems here, this is an equilibrium, because which side is entropy favoring? That way. We got maximum entropy here. Where's minimum enthalpy? This way. So this is what we're trying to overcome, is that particular equilibrium. We're trying to overcome the preference for this entropy and drive it that way. If you increase the temperature, you actually end up favoring the entropy. Which group hadn't got it? It was there. I feel like there's somewhere here. There. There. What did your group say? Anything else to add?
Not really. We had like increasing pressure.
No, okay. Anything else anybody can think of to do? Increase concentration. So constantly inject H2 and N2. And I kind of cheated here because I said it must be a closed system. And it is. But you can get the ammonia condensing on the wall. So if you can find a way and make it an open system and sort of have it drip out, so you're taking away product and adding reactants, then you can really start getting this reaction to go. So let's see how well we did. So find a catalyst, high pressure, low volume, inject N2 and H2, medium pressure to balance rate and equilibrium. Take away ammonia, so if you can make it less of a closed system, that would help. And so we got all the points. 12:52, it is time for your quiz. Put it away. And you will need to get out your own data tables, because I had them for you. Oh, no, I thought I had a bunch, but it turns out so many people have taken new ones and no longer have enough to use. Yep, you have to this time. I didn't put more because I thought I had a whole bunch, but it turns out I did not. Where did your... You'll need it more later when you have to look up things on tables. It's 12 marks. Where? It's 12 more text.
Can we leave if we're done?
Yep. I will tackle you. I did it to Gleb. I'll do it to you.
All tackled Gleb.
Yeah.
Oh, I saw that. What did you do that?
He tried to talk back.
Get away.
Oh.
I said he had to do his room because he failed, and he said something along the lines of, "You and what army?"
Wow.
Yeah. Well, he was joking. So I joked back by tackling him.
It's just no agreement for the right note.
Okay, I'm going to hand out your quiz so you can start. The answer sheets are here somewhere, and I will hand them out as soon as I find them. Separate out a little bit, like you're the one your bubble sheets. I'm going to grab them in a second, but I want you to be able to start it. I don't want to wait. No, you can start the quiz.